Hello, this is Mr. Henry, and welcome to Lesson 3.2, Transformations on a Grid. The essential question says, how do I represent transformations on a coordinate grid? The warm-up asks, how are dilations different than rotations, reflections, and translations? And hopefully what you've been able to see over the past, many lessons is that rotations, reflections, and translations are all those rigid transformations where the size of the image does not change, the shape of the image does not change. Where a dilation, on the other hand, the size does change. It's made bigger or smaller. It's zooming in or zooming out. Also, I want to mention, if you have not gone to seanhenry.org, there was an activity between the previous lesson and this lesson. So let me show you. So here's seanhenry.org, grade 8, module 3. So this was the activity or the lesson we just did. So there's this other GeoGebra activity about constructing dilations. Now this activity it might take a good while to do. It's multiple parts with interactive activities in there. I have 3 parts of this activity with directions, following through, doing stuff, moving stuff around. So go ahead and try that activity out. You might learn a good bit more about dilations through that activity. But let's go back on with the lesson. So here I just have vocabulary, since this lesson is going back to talking a little bit about each of them again. So starting with translation. Translation, if you remember, is when you slide or move the image from a starting location to a new location. A rotation is a turn or a spin. A reflection is a flip or a mirror image of each other. And a dilation is a grow or a shrink, a zoom in or zoom out. And we're going to be talking about these transformations on a coordinate grid, using X and Y coordinates, finding locations, finding different segments, those sorts of things. So the first part here says translations on a coordinate grid. In each figure, draw the required transformation. So I have here the first problem. Translate down 3, left 5. And I have this other little notation. This is another way that you might see a translation shown. So the X coordinate goes X minus 5. You're going left 5. Y goes to Y minus 3. You're going down 3. So in each of the images you're going to see, I have this one point kind of bolded, just to give you a place to start with. There's nothing special about that point. There's nothing particular about that point. It's just something to keep track of as you're doing your translation. So I'm going to go down 3, left 5. 1, 2, 3, 4, 5. That would be the location of this new point. It's going down 3, left 5. And each of the other points are going to do the exact same thing. Down 3, 1, 2, 3, 4, 5, left 5. Down 3, left 5. And then you can take your line and you can draw him in there. So that would be the image of this new figure. In example B, it says translate up 4. So this point's going to go up 4, and you see this other little notation. The X value is just X plus 0. It doesn't change. But the Y coordinate is Y plus 4. 1, 2, 3, 4. 1, 2, 3, 4. And you can just kind of follow and just use this. So I'm going to go diagonal 1, over 2, and back to the start. Each point should, though, follow that pattern of going up 4. So if I check from here, 1, 2, 3, 4. Check from here, 1, 2, 3, 4. It fits the pattern. These are all translations. I'm just sliding or gliding or moving one direction or another. I'd like you to please do this problem. It says translate down 3 and right 3. Go ahead, pause the video, try this on your own. When you're ready to continue, hit play, and we'll go through it together. Okay, so let's go. Here we go. I'm going to start at that point. 1, 2, 3. Oopsie. 1, 2, 3. Down 3 and right 3. Okay. And now, I mean, you can kind of almost sort of trace the image from here. I mean, this is going to go 1 that way. And then I'll pick another point. This one. 1, 2, 3. 1, 2, 3. So I've got down here, and then I go 2 this way, and then 2 down here, and then 3 this way, and then those connect. So there's my new image translated down 3, right 3. Pretty simple, pretty easy. Rotations, on the other hand, are not quite as easy. So here it wants us to rotate this image, this pre-image, 90 degrees clockwise. So clocks, the hands on a clock spin that way. So we need to go 90 degrees this way. A 90-degree spin is like that. So from here to here. If you think of like a clock going from 12 o'clock to 3 o'clock. 12 o'clock to 3 o'clock, or 3 to 6, or 6 to 9. Those are 90-degree rotations. So when I take this image and I do a 90-degree rotation, I'm going to move from the 12 to the 3. Watch what happens. This is actually what my image will look like when I'm done. It should be looking almost exactly like you see it right now. So what I need to do is I'm going to start here. Actually, I think this point is actually easier to start with. So this is the point 1, 1, 2, 3. 1, 3. When I do a 90-degree rotation, again, if you need to see it again, look where that same point ended up. It's right here. So that same point is going to go to 1, 2, 3, -1. And down, and over, and over, and up. This would be a rotation. Now this is rotated around the origin. And each of these are going to be rotating around the origin. I guess it doesn't say so in the picture, but that's what it is. It's rotating around the origin. So see if you can recognize how this point rotated 90 degrees. It's now here. So if it's on the x-axis, it's going to the y-axis. If it's near the y-axis, it's going to be near the x-axis. Rotate 180 degrees. Now it doesn't say clockwise or counterclockwise because 180 degrees is half of a circle. You're going to go over here. And if I went the other way, it would just be over here. Okay, so I'm going to rotate 180 degrees. First thing, and you can do this actually with your paper. If you put your pencil right here at this center point and kind of press fairly hard, and then take your paper and turn it around that center point, you'll see kind of an imagination of what this rotation is doing. So I'm going to rotate. 180 degrees is half of a spin. So the top of my paper is going to go to the bottom. So watch. Top, turn, 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 bottom. That's what my new image will look like when I'm done. It's going to be up here, facing this way. Let's put it back. Okay. So we know we know it's going to look something like that. So let's make more sense of it. This point right here, which is not really a point, it's just a location on this image, the opposite is it's going to be up here. See, it's kind of going to be like a mirror image. And so my first guess is I'm going to have something like that. That's this little nub that's sticking out here. Let's check. I'm going to turn this again. 180-degree spin. Boom. Look at that. It fits perfectly. And now all I have to do is just continue the image. So this goes 2 more here. This is the bottom. And then since this goes up 2, this is going to go down 2 and over 2. And then up 3. 1, 2, 3. And then the whole way over. And I can double check this. Now you can't do this on your paper, obviously. Have some of it stay the same and some of it turn. But that, well, it's pretty darn close. I mean, the center of this image may not be exactly at the origin. But that gives you an idea of what this rotation is doing. I personally find the rotations to be the most confusing in trying to find the original location to the new location. And I find that I'm always kind of double checking myself after I think I have it right, and I do my rotating and I spin. I check a couple of things 1 or 2 times before I even start making a drawing. But it's just one of the things that you'll get more practice with and you'll get better at. Go ahead and try this letter C. So you're going to rotate this image 90 degrees counterclockwise. So think the directions like the hands of a clock spin, and then go the other direction. Alright, so let's see here. Counterclockwise is that way. So I'm going to be going from 12 o'clock to 9 o'clock on a clock. This line is almost at 12, so I'm imagining it's going to be like here. And this is pointing away from the line, so I'm imagining something like this. Now this is just a quick sketch, don't make this. I'm just showing you imagining what this would look like in my head. Now I can actually start getting some of the details now that I know what it's going to look like in my head. So this is, here is that point. So I see, I went up 2 over 1, over 2, up 1. That is that 90-degree rotation. And now it's just a matter of filling in the image. So I go 2 this way, it's there. And to get these other 2 sides, let's see. I go up 1 over 1, 2, 3, 4. Well, that's going to be up here. So over 1, up 1, 2, 3, 4 takes me there. And there would be ugly. That's my new image. I rotated 90 degrees about the origin. Okay, next comes reflections. These are typically quite a bit easier. So the first one here, we're going to reflect about the y-axis. So everything you see over here, we're going to flip it over on the y-axis. So I'm saying this point goes here, this point goes here, and now I just kind of complete my image. I'm going to go 3 units this way, which is where that big bold point is, and I'm going to take 2 units this way, and then down 1, 2, 3, over 1, here. Now one thing that's kind of cool about a reflection is the distances on both sides of, in this case, the y-axis should be the same. So I'm going 1 here, 1 here. This is 1, 2, 3, 4 units to that point. 1, 2, 3, 4 units to that point. 1, 2, 3, 1, 2, 3. The distance on both sides of the y-axis is the same. That's why it's a mirror image about that y-axis. If you imagine taking your piece of paper and folding it right on that y-axis and pushing it together, those two images I've drawn here should exactly overlap each other on the folded piece of paper. And that's what a reflection is. Letter B. I'm going to reflect this about the x-axis, this line here. So all the distances are going to be the same distance away, but below. So 1 unit above, 1 unit below. Over here, 1, 2, 3, 4, 5 above, 1, 2, 3, 4, 5 below. And there we go. Here's letter C. I'd like you to reflect this about the x-axis. Go ahead, pause the video, and do it right now. Okay, so about the x-axis is this line. 1 unit below, 1 unit above. And then up 2. So I went up 2 more here. I'm going to go diagonal this way, or I can just do this. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And there we go. We have a reflection about the x-axis. So we've done rotations, reflections, and translations, which means the last one will be a dilation. Now, we did this in the last lesson. This is exactly what we did in the last lesson. It says draw the required transformation. So we're going to dilate about point O with a scale factor of 2. So I'm going to take each side here, and it's going to get 2 times bigger. So this has a length of 1, 2, 3. So my new length is going to be 1, 2, 3, 4, 5, 6. Double in length. And 1, 2, 3, 4, 5, 6. Double in length. There is my new figure, dilated about point O with a scale factor of 2. Everything is twice as big. Letter B. So there's my center O. I'm going to dilate everything with a scale factor of 1/2. So all the sides are going to be half as big. All the distances from the origin, or from the point O, to those corners are going to be half the distance. I'm going to start down here. Over 2, down 1, 2, 3, 4. Half of that would be over 1, down 2. Next, I'll do this big guy up here. Up 1, 2, 3, 4. So up 4 over 1, 2, 3, 4. Half of that would be up 2 over 2. That right there is actually enough information to make this rectangle. I know it's going to go up to here and over and down because it's just a rectangle, but let's do the other way. So up 4 over 2, which means I'd go up 2 over 1, and over 4, down 4, over 2, down 2. And there we go. We have our new image dilated with a scale factor of 1/2. And if you check each side length, 1, 2, 3, 4, 5, 6, 1, 2, 3. Each side is half of what it was before. The tall side here should be 8. 1, 2, 3, 4, 5, 6, 7, 8 units long. Here it's 1, 2, 3, 4. So I did use a 1/2 for my dilation. Everything is half the size it was before. If you could please do this problem. Now here I have a segment. I would like you to dilate that segment about point O with a scale factor of 3. Go ahead, pause the video, and do it right now. Okay, so let's see. Well, for me to get from point O to this point, I would go over 1, 2, 3, down 2. So if I take that and I do it times by 3, I'm going to get 3 times bigger. I'm going to go over 9 times by 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then down 6, because times by 3 is 6. 1, 2, 3, 4, 5, 6. So there's my new big point, this guy here, translated way out there. This point, well, times by 3, I'm going to go over 1, down 1. Times by 3 takes me over 3, down 3. And there we go. There is the same line, just made 3 times longer, scaled about that point O. And one more thing, just to show you here, you don't have to draw it, but remember this trick? If you connect out and connect out, look at that. They exactly match up. It's not a coincidence. It's designed that way. That is what we did. This length here and the total length here is a scale factor of 3. We went 3 times bigger. We followed the same directions 3 times. All right. Example 5, we're talking about applications of this same process. It says if trapezoid ABCD is translated using the rule, and I have there xy, x plus 2, y minus 4, if point D prime is at 3, negative 6, what would be the coordinates of point D? Okay, so it might help to make, you don't even have to have a good picture, just a little sketch. D prime is at 3, negative 6. So 1, 2, 3, 1, 2, 3, 4, 5. All right, so there's D prime at 3, negative 6. Now, the rule here said that from wherever you started, so here's some other point, my starting point, I went 2 bigger in x, 1, 2, and 4 smaller in y, 1, 2, 3, 4. So for me to get back to this original point D, all I'd have to do is reverse my directions. So if I go up 4, 1, 2, 3, 4, and left 2, what is the coordinate of that point? Let's see. If I get 2 smaller in x, takes me to an x coordinate of 1, and negative 6 bigger by 4, because we went up 4, would put me at negative 2. And that seems to fit with my little dinky sketch of a picture here. 1, 2, 3, 4, 5, 6, whatever. That seems to match what we said. Notice it doesn't tell us any other points about the trapezoid. All we needed to know was where this point is and the directions that it moved, and we can kind of do the reverse of this translation and find our old point, our original point from the pre-image. Here's one for you to try. It says line xy has coordinates x of negative 4, 2, y of 2, 2. If line xy is rotated 90 degrees counterclockwise, where would you find point x prime? I recommend drawing a picture, doing some rotating on your paper like I showed you with like putting your pencil at the origin and just turning the paper. But pause the video, try it on your own. When you're ready to continue, hit play, and we'll go through it together. Okay, so let's see. Here's my dinky sketch. There's just my xy coordinates. This has x coordinate of negative 4, 2, 2, 2. So this is the line x, y. And it says we want to rotate this thing 90 degrees counterclockwise. So we're going to be going that way. So if I take this image and I turn it like that, so that's about what my final image should look like. It should be with the y just above here and the x down here a little bit, but a straight up and down line. So I'm imagining probably something like here to here, x prime, y prime. All right, so let's see. That's kind of what I'm thinking in my head. If xy is rotated 90 degrees counterclockwise, where would you find point x prime? Well, x prime is this one down here. So if this point rotated that way, here it was 2 units above the x-axis, so it's going to be 2 units this way, which would be an x value of -2, and you went 4 units this way, so it's x of -4, the original image. So I'm thinking it can be -4 this way. Let's see if this point kind of matches what we think. So we think it should be this point down here. I'm getting jumbled. Green. Should be this point here. To get to that point there, I'm thinking if you go -2 in x and -4 in y, that should get you there. Based off my picture, I think I'm right. I know that's pretty confusing. Again, the rotations are the most confusing of the translations to get correct, to understand how it's rotating or moving. My recommendation is pictures, acting it out, actually turning your paper. There are little formulas, but you know what? For the most part, they're more complicated than just trying to turn your paper. And there's like 2 or 3 different little formulas that might help you pop some of these numbers into a little form and spit out an answer. Letter C. It says triangle ABC with coordinates A of 3, 4, B has coordinates 4, 8, and C has coordinates 3, 2 are reflected across the x-axis. What are the coordinates of the image A prime, B prime, C prime? Okay, so sketch, definitely in order. Boom, boom. 1, 2, 3, 1, 2, 3, 4. There's A. C is 1, 2, 3, 1, 2. There's C. B is 4, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. And there's B. So my image is something like that. So if I flick that across the y-axis, it's going to go that way. So all my y values, the height of each point, is going to stay the same. So this C value has a y value of 2. C prime is going to have a y value of 2. It's just going to be over here. Same thing with A prime and B prime. So A prime, B prime, C prime. I know the y values are going to stay the same, because all they're doing is I'm moving this point that way. It's not going up or down at all. So B has a y value of 8, C has a y value of 2, A has a y value of 4. I'm just using this. B is 8, 8. C is 2, 2. A is 4, 4. And since I'm reflecting across the y-axis, C, this bottom guy here, he was at 3, 2. So he was 3 units this way. So if I go 3 units that way, puts me at -3, 2. And same with each of them. A was 3 units this way. So A prime would be 3 units less than the y-axis. 3 units less than 0 would give me -3. And B would be a -4. That looks like a 9. So those are my coordinates. An image helped out, helped me understand what was going on. I recommend you draw a picture. Last problem of the day. It says triangle JKL is going to be dilated with a scale factor of 3 about point K. So K is the origin or the center of the dilation. Okay. If coordinates JKL are J is 5, 8, K is 5, 2, and L is 1, 5, what would be the length of KL prime? And what is the perimeter of J prime, K prime, L prime? And I have this listed as a DOK3 because it is an in-depth problem. It's going to take multiple steps. It's going to take some time. So pause the video, try it on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so first thing I'm going to do is I'm going to make a sketch. So J is at 5, 8, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Actually, all the numbers are positive. Cool. So 2, 4, 5, 8 is like here. That was J. K is at 5, 2. L is at 1, 2. This is our shape. That's K. There we go. All right, so it says the points are going to be a scale factor of 3 about point K. So this K right here, it's gibberish in here now. This point K is everything's going to be getting bigger and smaller from here. This is the point where they're zooming in and zooming out from. So I have to find out how big each one of these segments are and then times it by the scale factor of 3. So this I'm not going to do that one first. I'm doing KL or LK. They have the same Y value. The X value is different by 4, which means the length of LK is 4. Now, if you can't do that using the formula the way I've done it, that's fine. What you could do is the distance formula from the last module. Do you remember that? Distance equals the square root of x, not squared, x2 minus x1 squared plus y2 minus y1 squared. That is the distance formula. You could use that exact same thing, and you could find the length of this KL prime that we're trying to find. You could use this to find the distance, and then all you do is take that distance, times it by the scale factor of 3, and you get your answer. But I can tell by looking at my pretty picture, because it's an okay sketch, that this has a length of 4. So since the scale factor is 3, my new length would be 4 times 3, or not K prime L, KL prime would be 4 times 3 is 12. This new length, 3 times bigger, would be 12. So first part of the problem, not too bad, not too hard. You could have used the distance formula to find out how long it is, and then take that distance times by 3, you get 12. This one's a bit more tricksy, though. It says, what is the perimeter of J prime, K prime, L prime? So we need to find the new image. So I know this new image, this bottom side is 12. We found that in the last problem. What I don't know is how long that side is and that side. So I have to find this JK as well, or J prime K. So let's see, JK, the original length here, went from a height of 2 to a height of 6. Nope, I lied. 8. From height of 2 to a height of 8, which gave me a distance of 6. So if I take that distance and I multiply it by the scale factor, I get my new length is 18. All right. Everybody following so far? We could have also, again, we could have used the distance formula, plugged in the points of, let's see, what am I doing? I'm doing j and k. I could have done d equals the square root of the distance from j to k. All right, so we got 5 minus 5 squared plus 2 minus 8 squared. That gives you 0. That gives you negative 6 squared. D equals the square root of 36. D equals 6. That is the distance from j to k. And then you take that times by the scale factor of 3, so the distance from j prime to k is 18. So just showing you, yes, the distance formula works. It's just fine to use. It might even be the way that you did the problem. But to find the perimeter of j prime, k prime, l prime, we need to know how big all three sides are. We found this side is 12, that side is 18. We need to know how big this side is. If you have not made an attempt at this part yet, if you got stuck somewhere along the way and I'm caught you up now, maybe pause the video and try it on your own. If you tried it and you still don't get it, well, here we go. So a trick that I see here is that this is actually a right triangle. Looky. From my original image, this line is straight vertical up and down. JK is horizontal, which means that is a 90-degree angle, which means this is a right triangle, which means I can use the Pythagorean theorem, plugging the numbers 12 and 18, and find the length of this side. Love it. The other way you could do it is, now that you know what this distance is, you could go from 2 up 18 units and find this has a coordinate of 20. I should say it's 5, 20. There, 5, 20. And this point over here, since you know the length is 12, you'd go 12 units from 5, and that would put you at negative 7. So it would be negative 7, 2. And then you could use the distance formula on that again and find that length. But I like my way better. I like this Pythagorean theorem. A squared plus b squared equals c squared. By the way, Pythagorean theorem, it's not going away anytime soon. You're going to see it quite a bit more throughout the rest of the year. So don't forget that thing. He's big in 8th grade. A squared, 12. B squared, 18. C squared, my missing side, because that is my hypotenuse. 12 squared is 144. 18 squared, have no clue, but it ends in a 4. 18 squared, 324. C squared, add them together. Let's see, plus 144 equals 468. Equals c squared. Last thing we've got to do is square root each side. And that gives us the c value of 21.633338. 21.63. That is the length of letter C. Alright, are we done? Did we answer everything we should have? No. We did not actually tell what the perimeter is yet. Our job here was to find the perimeter of JKL. We now know all three sides. Since we know all three sides, we can find the perimeter. So the perimeter of this J prime, K prime, L prime thingy is going to be 12 plus 18 plus 21.63. $21.63 plus 12 plus 18 equals 51.63. That is the perimeter that we were looking for. Always keep the original question in mind. What is my goal? My goal in the second part was to find the perimeter. So my driving thought throughout this problem, I didn't voice it, I guess I should have. My driving thought throughout this problem was, I need to find how big each side is so that I can add them together to find the perimeter. So I knew from the first part of the problem that this bottom side was 12. So I knew that was 12. So my next goal in my head was to find out how big these other two sides were so that I can add them together to find the perimeter. My driving goal was to find the perimeter. I needed the length of all the sides, so I did my work to find the length of all the sides. Now I can add them together, and there's my answer. The perimeter is 51.63. That, dear boys and girls, is a complicated problem. Very in-depth, took quite a few steps to do. But it's nothing new, nothing we haven't done before. If you could please, summary. How do you represent transformations on a coordinate grid? That's kind of a summary of the whole lesson. So how did we do this? Go ahead and answer this. This, I think, was the essential question. Go ahead and answer it in the best detail you can. We're ready to continue. Hit play, and we'll go through it together. Here's what I came up with. I say to represent transformations on a coordinate grid, you need to know the x, y coordinates of the points, which is true, you do. Then it helps to act out the transformation in your head to get a good idea of where the new image will be. That's especially true when we were talking about the rotations, how I told you about putting your pencil down and turning around the origin or around that point. It's also good to think about the acting out of the dilation. Like if you imagine like zooming out, the image becomes smaller. Or if you imagine acting out a translation where it shifts, either just moves left or right or up or down. Or even the reflection, imagining what it would look like if you flip it across the y-axis or the x-axis. Finally, make your measurements and draw. Finally, after you know where it should be and what it should look like, you make the appropriate measurements, and then you draw your new image. This has been lesson 3.2. Thank you for watching.